speaker, the Professor Gannon from Peking University's Beijing International Center of Mathematical Research. The top topics about model theoretic dynamics and the Newelski conjecture and beyond. Kyle, it's yours.
Thank you. Thank you so much for inviting me, and thank you for letting me talk. So, so the topic of my talk today is so the model theoretic dynamics, the Newelski conjecture and beyond. I mean, hopefully, we'll get to the Newelski conjecture, but somehow, I mean, the purpose of my talk, right, is that there's this connection between model theory and dynamics, and actually, it's really nice, right? So there are these invariants that you can compute in dynamics. And it turns out that actually, like, in some cases, they're the same as the invariants that you care about, say, from the model theoretic point of view. Oops. So, so the purpose of this talk is to survey some machinery results and problems, say, in model theoretic dynamics, right? So, if you don't know what this is, I mean, you'll see during the talk. So the outline is as follows. So first, we'll recall some background in topological dynamics and semigroup theory. So for this, you'll need to know nothing, no model theory, no anything. Then we'll discuss, maybe group actions in model theory, right? Like the objects that we actually care about. And then if you know, I mean, it gets a little bit more complicated. We'll discuss NIP theories. If you've never heard about NIP, well, it's just some tameness property of theories that you can have. Then we'll discuss maybe the Newelski conjecture, and then at the end I'll give some open directions, maybe some current trends in the field. And also, like, I tend to go very quick and speak too quickly, so if you need me to slow down, or please just say something, because I know I go very quick. So, and I should say, right, that a lot of people have a lot of important ideas, maybe in this vein of model theory, right? So Newelski, Pillay, Krapinski, Chernikov, Simon, Szepetsky, and then Ningyu and Yao, right, as well as many others, right? So I forgot tons of people, but somehow these people have been maybe very influential in the way that I think about this subject. So, so for the purposes of this talk, right, so a dynamical system is just going to be a triple. So we'll have where X is a compact Hausdorff space, G is a group, and pi is just an action of G on X by homeomorphism, right? So I have some space, and G is acting on it by just homeomorphism, right? So I will usually write, say, XG pi just as XG, right, where my action is implicit. So I'll forget about writing down the pi, right? I give you a group, I give you a space, there's an action, right? Something like this, And so, so suppose that I have a dynamical system, say XG, then the system, say, emits a natural compactification, right? So I have some, right? I mean, in my definition, I have no topology on G, right? But it turns out that actually, in general, any type of group action like this will emit, say, a natural compactification. So how does it work? Well, so the first thing that I do is I consider the space of all functions from X to X with the product topology, This, as we know, is a compact Hausdorff, it's a compact Hausdorff space. It's also a semigroup with multiplication given by just composition of functions, right? These are just all maps, right? I can just compose them. I still get maps, right? Then I consider the embedding of G into this space, right? How does it work? Well, for each element G, I associate the homeomorphism that it acts on X by, right? So this is a map from X to X. Right? So I can consider this set living inside the space. Right? Then the trick is to take the closure, right? The object that I care about, the Ellis semigroup of this group action, is just taking the topological closure of this embedding inside this space, And in general, right, I mean, I write the semigroup as E of XG, So the takeaway, right, is that if I start off with any dynamical system, can you see my cursor when I do this? Can you see this? Yeah. So if you start off with any dynamical system, with the caveats that I said, you can associate maybe a compactification that's a semigroup, right? Some type of semigroup. And so, we remark, and this will come up later, that this object, right, this semigroup that I get is a left continuous compact Hausdorff semigroup, right? So it's compact Hausdorff, right? We know what this means. Left continuous means that when I multiply on the right, all of these maps are continuous, right? So I'm not going to get joint continuity, and I'm not going to get separable continuity, but I will get that when I multiply on the right, this will always be continuous, okay? And it turns out that these semigroups have a lot of nice structural properties, okay? Okay, so suppose that I have a dynamical system, say xg is just some dynamical system. Now, okay, I mean, to a dynamical system, I can give you some invariants. And the point is that, okay, they're going to be the same as some semigroup invariants, and it's easier to compute the semigroup invariant than the dynamical system. But okay, I'm getting ahead of myself. So suppose I have a dynamical system. Then if I give you a subset of the Ellis semigroup, I call it a subflow. Okay, in general, okay, it's different, but in this case, I'll call it a subflow. If it is closed, right, it's a closed subset. And for every element in my group and every element of B, when I hit F with this element, it stays inside B. Right? So it's the flow is staying inside this subset. Okay. And we say that B is minimal if there does not exist a proper subflow. Right? So there's no subset of B, okay, that's non-empty and has this property of being a subflow. Right? So the minimal subflows are the important ones. Okay. And okay, look at that. And the minimal subflows are an important invariant, say, of my dynamical system, right? So it turns out that these things are really kind of the I don't know what's maybe a good idea. Like somehow it's if I'm thinking about my dynamical system, the minimal subflows are really the rocks or something, right? If I'm thinking of like, I don't know, a river, like the minimal subflows are really like the hard things that I can think of. Okay, they're the invariants. And in fact, what makes everything a little bit easier is that the minimal subflows correspond to minimal left ideals coming from semigroup theory. So if instead of thinking about dynamical systems, and I kind of just make it more algebraic in the semigroup side, then it's somehow, they're really just minimal left ideals. And this is somehow easier to work with. So, okay. So you don't need to remember any of that because we will be thinking on the side of semigroup theory. But okay, so let's recall some terminology from this side. But okay, I mean, the reason we brought that up is because that's where the motivation comes from. Right? So suppose that Y is a compact Hausdorff space, and I have that Y with a star operation is a semigroup. Yeah. Okay. Then I say that a subset of Y is a left ideal if it is closed, right? This is a compact Hausdorff space. I can talk about what it means to be closed. And I have that Y times I is a subset of I. Okay, so it means to be a left ideal, right? So when I take the whole space and multiply it against I get something inside I. Right? So we say that I is a minimal left ideal if I is a left ideal, right? And it does not properly contain any other left ideal. Right? So same idea as being like a minimal subflow. Okay. And what's important is that, okay, we say that Y star is left continuous. If anytime I look at some P inside Y, I have that this map, right, multiplying on the right is continuous. And then finally, the last kind of formal definition I need is if I take any point in Y, I say that it's idempotent if when I multiply it against itself, I get itself, right? So it acts kind of like an identity, okay? And so connecting maybe the two pictures, right? From my definition from the previous slide, we have that B is a minimal subflow of this space if and only if B is a minimal left ideal of this semigroup. Right? So these two things are somehow, okay, I mean, they're the same. Right? So somehow we can just study maybe from the algebraic perspective and things are a little bit easier to work with. Okay. And as I said earlier, right, the things that we really care about are these minimal subflows or these minimal left ideals. And it turns out that there's this somehow amazing theorem, right? That just totally classifies what minimal left ideals are supposed to look like, right? So the minimal left ideals of left continuous compact Hausdorff semigroups, right? Okay, I know this big collection. They emit a very strong decomposition theory. Okay, and okay, remember that these are somehow, right, the things that we really care about, and it turns out that they actually look very nice. Okay, so what do they look like? So it's an old theorem. Okay, Ellis Nairukar, right? So suppose that y star is a left continuous, say, compact Hausdorff semigroup. Okay? And let I be a minimal left ideal of y. Okay? Then there exists some element in I such that this element is an idempotent. So u times u is equal to u. So no assumptions, right? I take any left continuous compact Hausdorff semigroup, I get an idempotent, right? From nothing. Okay? Number two, it turns out that if I look at any idempotent in my minimal left ideal, right? So all of my minimal left ideals contain an idempotent. If I look at any idempotent and multiply it against my minimal left ideal, I get a group. Okay. Moreover, this group does not depend on any choice of minimal left ideal or any choice of idempotent living in a minimal left ideal, right? So these things are isomorphic as abstract groups. And so, okay, I mean, it's amazing. Just having a minimal left ideal, I get all of these groups, and they're all isomorphic, right? So you can define, right, the ideal group of the semigroup, right, to just be the isomorphism type of u times I. Okay. Now, the amazing thing is this last one, right? So it turns out that this minimal left ideal, right, this minimal subflow is literally a disjoint union of its ideal subgroups, right? So more explicitly, right, if I let I of D be the collection of idempotents in I, then I can write I just as a disjoint union of groups. Okay, this is somehow the miracle, right? So you just start with, right? You just start with some, you know, just totally abstract left continuous compact Hausdorff semigroup, and the things that you care about, right? These somehow invariants, these minimal left ideals have a very strong decomposition theorem to all these groups, which are all the same. They're all isomorphic. Right? So what does it look like? Right? This beautiful picture. Right? So we start off with our say this a whole space is my semigroup. This I here is my minimal left ideal. I have a family of idempotents, right? And I know that I can write I as a big disjoint union of all these groups, right? Ui times I, and all these groups are the same, right? So I've taken my semigroup, or okay, if you don't like semigroup theory, you have your okay, I mean you have your minimal subflows, right? And I've been able to decompose it, say, into a bunch of disjoint groups that are all the same. Okay. So very nice decomposition there. Okay. And so one important takeaway, right, from this is that from a dynamical system, say XG, one can associate, say, a canonical group object, right, to the ideal group of my Ellis semigroup, right? So remember, we started with a group acting on a space. Then I built this semigroup, right, this compactification, and I know that this is a left continuous compact Hausdorff semigroup, so it has a group object, right, this ideal group, right? The the isomorphism type of any of the u times i's. So I'm saying one of these people, okay? Right? So you start with a dynamical system, you get somehow a very important maybe group out of it, right? So, okay, part one is done. That's semigroup theory. So now we can move on to part two, which is say group actions in model theory, right? So, okay, how is everything connected? Okay, so group actions say arise maybe in two natural settings in model theory, and today we'll discuss one of them. But okay, there's two natural settings, and the first one is the following, right? So if I give you let's say I have some language, right, that has multiplication, has an identity, and has inverse, right, and G is an L structure, which, okay, is a group. Then G acts naturally on its type space, okay? How does it act? Well, okay, if I take any element of G, I want to multiply it against a type and get a type. Right? So this is how the action works, where G times P is going to be, okay, formally, this is how you work it out correctly so that you get the correct type. Right? It's because you want, when G acts on the type of the realized identity, you want to get G, and this is how you do it. Right? So we claim that for any, say, G and G, this map is a homeomorphism of my type space, and so I get a dynamical system. Right? Okay. Now, there's another type of group action that comes up maybe quite often in model theory. And if I start with, say, any language, and M is any model, then the automorphism group acts on my type space, where, okay, how does it work? Well, pi sub sigma of P is going to be sigma of P, which, okay, all it does is it just permutes my parameters, right? That's what it's doing. And again, we have another dynamical system, right? It shows up, say, naturally inside model theory. And okay, both are interesting. Both have like maybe a lot of things that one can say about them. But today we're only going to focus maybe on the first kind. So we're not going to think about maybe automorphism systems, but we'll think about groups acting on their type space. Okay, and there's some. Okay, it would be great if we could just study these actions and be like, great, everything works, things are nice. But unfortunately, one has to change the model a little bit. So in general, maybe small models can introduce maybe noise or pathologies. And to fix off, right, if I choose a random model, its type space might not be very good, right? And so to ward off, say, these problems, it's usually advantageous to work over, say, a monster model, right? In the setting of a monster model, right? So what is a monster model? Well, it's just some big saturated model, right? That has many, many points. Okay, so instead of acting on, say, the types over G, we act on, say, a larger space, which can be thought of as, say, maybe the logical completion of G relative to, okay, its monster model. I mean, we can maybe delete this. I think maybe it's better to just think about is some type of logical completion. Yeah. So how does it work? Well, if I let, say, G be a monster model, and okay, take G as maybe a small elementary submodel, then I say that a global type, right, a type over my monster model, right, is finally satisfiable in my small model G if for any, say, formula inside my type, there exists some little g in G such that big G says, oh, that formula is satisfied. Okay, so every formula in my type has a solution inside my small model. Okay, that's what it means. Okay, so I have this funky notation, but okay, we let this notation just denote the collection of all types, right, in my big model, which are finally satisfiable in my small model. Right? So this is what we're going to think about as the completion. And so, okay, in some real sense, it is the topological completion. Yeah. So this space of global finally satisfiable types, right, types over my monster, which have this nice property, is literally the same as just taking the closure of my realized types inside my small group. Yeah. So it really is, in some sense, a completion. And okay, if you know what stable means, if T is stable, you don't need to do any of this. It's all the same. You can work over the small model. There's no problems. It's only when you need to work outside the stable context that you have to worry about maybe working over maybe a monster model. And then finally, I should say that G acts naturally on the space of global finally satisfiable types by homeomorphisms, right? And the action is defined similarly as the action I did before, where I have G acting on the space of types over G. Okay. And so, okay, maybe this is a little too complex, but the slogan is that one should think about maybe the space of global finitely satisfiable types as types which are in some sense close to the model, right? So somehow it's the completion of the model inside this larger space. It's somehow the collection of types that are very close to my original model, G. Okay. Okay. So it turns out that actually the space of finitely satisfiable types form a semigroup. Okay, I need to be over a group, but actually it already forms a semigroup. You know? How does it work? And okay, here's the definition. It's okay. I'll read the formal definition and then we'll see really kind of the slogan, right? So I take two global types, which are finitely satisfiable in G. Then I have that a formula is in their product if and only if my monster model says that this formula holds, V of A, B, where B is a realization of Q and A is a realization of P. Okay, formal definition, fine. What's the idea, right? So P star Q is the generic product of P and Q, right? I'm living over a group. I'm saying that it's the generic product of realizations of types. So the idea, right, is first we realize Q, then we realize P over the realization of Q, right? So we realize Q, this is what B is. Then we realize P over the realization of Q, that's what A is. We take their product, A times B, and then we just take the type. That's the idea. So it looks like this. You go boop, boop, take their product, and then you take the type. Okay. And so amazingly, somehow amazingly, right? This forms the type of semigroup that we care about, right? This forms, say, a left continuous compact Hausdorff semigroup, right? So it's compact Hausdorff space, and it's left continuous. So you need to check this, but okay, this is not very hard. Right? And somehow the miracle, right, is actually, this is precisely the space that we care about, right? So if I take the space of finitely satisfiable types and have this Newelski product, right? This product that we defined in this previous slide, this is the same as looking at the Ellis semigroup of the action of G on the global finitely satisfiable types in G. Right? So I know. It's the left-hand side's a little, or excuse me, the right-hand side's a little bit, you have to think through it, right? I just have my group acting on this space. I do this Ellis semigroup construction. It's the same as this product that was defined on the previous slide. Now, I mean, the right-hand side, like computing anything, that's a nightmare, right? I mean, somehow dynamics is hard, right? Semigroup theory is easy. And somehow you should really be reading this as going from right to left, right? This space can be simplified by thinking about this space. But it's a really kind of amazing observation, right? And okay, I mean, the proof isn't too difficult. One needs to show that the map, right? So remember that this is a space of functions, right? From this space to itself. And so the map sending P to P star blah is an isomorphism. Okay. So, okay. I mean, and okay, much more is known maybe when you're in the stable context, right? So if T is stable, then actually, like I said before, you don't really need to work with more points. That's what this is saying, right? So if I'm computing maybe the Ellis semigroup of G acting in its space of global finitely satisfiable types, okay, this is the same as just looking at G acting on its type space. Okay, the easier thing. So moreover, if you know anything about maybe topological dynamics, this space this action is weakly almost periodic, and in particular, it's separately continuous. So multiplying on the left and multiplying on the right are both continuous things. So it's very nice. Right? It's a very nice thing, and it fits our intuition that stable things should be nice. Okay, and the proof again isn't very hard. It follows from the fact maybe our first theorem here, right? And then the fact that all types are definable in the stable setting. So we know, as model theory people, we know many things about this space. And by using the fact that all types are definable, one can prove that we know things about the dynamics of this space. So it's a very nice kind of transfer. Okay. And so, okay, this leads us to say kind of the main question of today. And okay, the question is, what is the ideal group of this action? Right? So as we were saying before, right, okay, I can look at this LSME group. I have this object, but really to the LSME group, I can identify a canonical group object. And the question is, what is the ideal group of this action? Right? Okay. And this leads us to part 3. Right? So cliffhanger, yeah. So an interlude on NIP theories, right? So okay. Okay, so maybe you haven't seen NIP theories before. Maybe you know many things about NIP theories, but okay. For ease of notation and presentation, I'll let X and Y say denote tuples of variables, and L be a language. So this has nothing to do with dynamics. This is just totally model theory, right? And okay, why am I bringing this up? Well, let me just say, so this question has been answered for a particular family of structures. And this family is relatively tame, it's relatively nice, and I want to give some background on what this family actually is. And it's, okay, I mean, I don't want to spoil it, I mean, we'll get to it, but it's some collection of NIP groups, right? So, okay. So, as I said, for ease of notation and presentation, say X and Y will denote, say, tuples of variables, and my language will always be, say, countable for now. Right? So if I fix an L structure M in subset less than A, okay, we say that a partition formula, phi of xy, shatters A if for any subset of A, so A you should be thinking about as a finite subset, and I want to encode it with a parameter. Right? So for any finite subset of A, excuse me, for any subset A and any subset of my subset, I can find a B which cuts out K. So every subset of A is cut out by a parameter. Okay, that's what it means to be shattered. Right? And don't worry if we're not going to harp too much on this. Yeah. So we say that phi has the independence property. If my formula, phi of xy, say shatters arbitrary large finite subsets of M. Right? So okay, if you can do this thing where you take a finite subset and are able to somehow cut out every finite subset of the finite subset, you have the independence property. Okay. And so notice that this only depends, say, on the theory, right? It doesn't depend on the model, and therefore you can say that phi xy has the independence property with respect to the theory, right? In your particular language. Okay. And we say that a formula says NIP with respect to T if it does not have the independence property, right? So, and then you have this thing that happens a lot where, okay, people say not NIP, right? But you shouldn't say not NIP, right? You should just say IP, something like this. But okay. So there's this definition, combinatorial dividing line. It's not very important what it actually says for the purposes of this talk, but the idea that there is this dividing line is important. So we say that a theory is NIP if every formula says NIP with respect to T, fine. So what are some examples of NIP theories? Well, okay, so all stable theories. So if I look at C, if I look at algebraic groups over C, but also things like the reals, definable groups in the reals, definable groups in the p-adics, right? So all these things are going to be NIP. Also things like linear orderings, partial orderings. These are all NIP-like things. You should think about it as maybe, okay, orderable things, and then also, okay, yeah, something like this. Non-examples include maybe, okay, piano arithmetic. So like the idea x divides y is going to have the independence property. Something like the random graph also has the independence property, right? It's where I have my formula, just the edge relation. And then one of my favorite examples is if I just look at, say, an infinite product, right? Oh, sorry, this should be a sum. It should be a direct sum. The infinite direct sum of S3, which is just the permutation group on 3 elements, right? This is IP. The formula xy is equal to yx has the independence property, right? And okay, you don't need to take S3. It's true for any non-abelian group. But S3 is the first, it's the first non-abelian group, right? There's no smaller non-abelian groups. Is this right? I think so. Yeah? I think so. Yeah, so okay. Okay. Okay, so let's collect everything that we've talked about today. And so, okay, this last section, excuse me, okay, I guess formally second to last section connects maybe an object called G00 and the Newelski conjecture. So remember, we have some group acting on a space of types, and we really want to know what the ideal subgroup is, right? And so, okay, we need to discuss something called type definable subgroups, right? So if I have a group and I have a formula, I can define a subgroup, and this is called a definable subgroup, fine. But a type definable subgroup is something that you can build with maybe infinitely many formulas. So let A be a small subset of my group G, right? G is my monster model. We say that a subgroup, say H of G, is type definable over A. If there exists a family of formulas, so phi's, each in say Lx of A, such that, okay, B is an H, if and only if it satisfies each of the formulas. So I'm giving you a big definition. It's not just a single formula, infinitely many formulas. Right? Moreover, we say that H is bounded index, excuse me, if the index of H inside G is small relative to the cardinality of G. And okay, small, what do I mean by small? Well, if we think of G as being some very big monster model, like maybe class size, then the index should be set size, right? I mean, you can formalize this, but I think somehow this is somehow the better idea. I think it's actually like bounded by something like to the blah, something like this. Something actually you can write down, but in my brain, I mean, this is somehow the picture. Yeah. So we let this G00, right, be the intersection of all type definable subgroups of bounded index over A. Yeah. So it itself is going to be bounded index, and it's okay. I mean, it's a subgroup, right? The intersection of subgroups is a subgroup. I'm building some subgroup. Yeah. And so, as I just said, right, somehow GA00, right, is the smallest, say, A-type definable subgroup of this of bounded index, right? So what does this mean? It's just giving a first order structure, which is a group. I can give you, and I give you a set of parameters, right? I can get somehow this smallest connected component, this smallest subgroup, right? This rock, right? So what's the point? Well, the point is that there's this really nice theorem by Shelah that says that if you start with, suppose that T is NIP, then for any small subset A of G, when I build G00, right, when I look at the intersection of all type definable subgroups, it's the same as just doing it over the empty set. So it's really a canonical part of my theory, right? It doesn't depend on parameters. It really just depends on my theory. Yeah. And okay, it always exists in NIP theory, right? And the second point is that when I look at my whole group modulo this kind of canonical subgroup, right? Since it doesn't depend on any parameters, right? This is a compact Hausdorff group under the so-called logic topology, right? So it's the isomorphism type of this group, say, does not depend on my choice of monster model, right? So the takeaway is that maybe from an NIP group, I can also define, say, a canonical group object, right? So remember at the beginning, I started off with a group acting on a space, thinking about a dynamical system, and I got a canonical group object. Here I'm starting off with, say, an NIP group, and I'm also getting a canonical group object. Okay. So given an NIP theory expanding a group, say, okay, as I just said, there's a canonical, say, compact Hausdorff group associated to that theory, right? Namely G mod G00. Okay. 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 So I have these examples. I mean, I was a little bit, how much time do I have? I still have like 15 minutes. Okay. So we don't need to do these examples in depth, but I just want to give a flavor of what G00 looks like, right? Because it's something that you can actually think about. It's not some strange thing. So if I think about the circle, say, as a group, and I think about, say, with maybe a circular ordering, okay, my plus is just saying that it's abelian, right? I'm thinking about the circle as a group, right? And I have G as my monster model. Then, okay, if I look at, say, 0, this is a type definable subgroup, but it's not a bounded index, right? The index is very large, right? It's the whole space. It's the size of G. But here's a type definable subgroup of bounded index, right? I can just look at, say, all of the intervals around my identity, right? And I take their intersection. This is going to give me a type definable subgroup of bounded index. So I've just drawn this beautiful picture, right? Here's my circle as the group. Here is my intersection of all my, say, type definable subgroups, right, around my identity. These are all okay. These alphas need to be, these are real alphas, right? Just real numbers. Yeah. And so the point is that what is my canonical group object? Well, it's just S1. When I look at this quotient, right, I actually get, I'm just quotienting out by the infinitesimals, and I just get my original group back. Okay. Now this is different than if I look at the reals, for example. In the reals, I can look at, say, this infinitesimal subgroup around the identity, but it's not bounded index. And it turns out when I do G mod G00, it collapses to a single point. Okay. So, okay, yeah, I mean, maybe it's a little bit hard to see why this is true, but somehow these cases are different. Yeah. And then the last example, maybe that one should think about is, okay, I mean, you start with S1, you get back S1, you start with the reals, it's kind of degenerate, it collapses. But I think somehow a really interesting example is when you look at the integers. If I look at Z, this is an additive group, then I can always give you a subgroup, say, of index n, right? This is bounded index. It just says that I'm NZ, right? But I'm in my monster model, right? So I'm elements that are divisible by n, right? And G00 is the intersection of all these people. And when you quotient, you get Z hat, right? So you get the profiling completion of the integers, right? So this is okay. This is, I think, like a really good example of the group that you get to, the associated group to say maybe Z, you know? Okay, so these are just some examples. I know that they're kind of hand wavy, but you can compute these things. That's kind of the argument I'm trying to. Okay, so we're now at the Newelski conjecture. Yeah. So what is the data? So as I said before, if I give you a dynamical system, it admits, say, a canonical group object, right? This is the ideal group. So I start with my dynamical system, I got the LS semigroup, and then I get my ideal group, right? And on the other side, if I start with an NIP theory, say expanding a group, then it also admits, say, a canonical group object, right? G mod G, this should be G00, excuse me. Yeah. Okay. So that's the question, right? What is their connection? I have these two canonical group objects, and the question is, how are they related, right? And somehow, okay, the most basic question that you can ask is, suppose that T is NIP, theory expanding the group, then the ideal subgroup of my group action, right, of my Ellis semigroup of G acting in a space of global finitely satisfiable types, this is isomorphic to G mod G00, right? Now, it would be great if this was true, and I could say, oh, yeah, that's the story, but it's false, right? The Newelski conjecture is not true. Yeah. And the counterexample is kind of nuts, right? I mean, it's a little bit, it takes some work, right? So the counterexample is the ideal subgroup of, if you look at SL2R, right? And I have SL2R acting on its space of types, when you compute its ideal group, you get Z mod 2Z, and G mod G00 it collapses. Yeah, it collapses, right? So there's no type definable subgroups of bounded index, right? There's no non-trivial type definable subgroups of bounded index. Yeah. So okay. Well, okay, you could say. SL2R is large in some sense, right? So what type of sense is it large in? Well, it's large in the fact that, say, it's not amenable, right? It's not an amenable group. So this is some notion of largeness. And so there's a revised version. There was a revised version of the Pillai conjectures, and says the following, right? Suppose that T is an NIP theory expanding a group. Moreover, right, assume that T is definably amenable, which, okay, I'll say what this means in a second. So as I said, amenable here is some notion of smallness, right? So non-amenable means you're big, but definitely amenable means somehow you're small. Then the ideal group of this thing is isomorphic to G mod G00, right? Then these things are actually the same. And this is true, right? So this is the kind of kernel, the very nice kernel of truth, right? So okay, so I should tell you what it means to be definably amenable. It means that you're small, right? But in some sense, it means that you emit an invariant measure. Yeah, you're somehow okay. One way is saying that you're small. Maybe another way is saying that you don't have like a paradoxical decomposition, right? You're somehow manageable. So let G be a model of T. Excuse me. T is a group, right? T is a theory expanding group. We say that G is definably amenable if there exists a left invariant Keyser measure, just some measure on some finely additive measure on the formulas with parameters from G, right? So on the definable subsets of G, right? More explicitly, right? There exists, say, a finely additive measure. Oh, I say it right here. Mu on the definable subsets of G, such that, okay, for any formula, right, mu of phi of x is the same as mu of phi of G times x, right? And I'm in a group, so I have some multiplication I can write. Yeah. I should say this measure should be a probability measure. So this isn't written, but it has to be zero, valued between 0 and 1. Measure the whole space is equal to 1. Yeah. And so, okay, it's not hard to see if G and H are elementary equivalent, and I know that G is definably amenable, then H is also, say, definably amenable. Yeah, this is maybe an exercise. And therefore, right, so you can say that T is definably amenable if, okay, there exists, or for all of its models, they're all definably amenable. Okay? Something like this. Yeah. Okay. And so kind of the right, I mean, it's called the Newelski conjecture, or maybe the Newelski-Pillay conjecture, but it's a theorem. It's a theorem of Chernikov and Simon that this is true, right? So suppose that T is NIP and definably amenable, right? It's a theory of a group. Then the ideal subgroup of this action, this LSME group, is isomorphic to this this canonical, say, model theoretic invariant, right? So an invariant just from dynamics, right? Excuse me. A dynamical invariant is the same as a model theoretic invariant, right? This is somehow the content of the theorem, right? Is that people in topological dynamics and people in model theory, okay, when you study very particular systems, you're really looking at the same thing, right? So, okay, what is the proof? Well, okay, I mean, this is not really a proof, but this is the idea. You look at, say, SX, the global types which are finally satisfiable in G, and I have a map, say, from this space into G mod G00, where I can just send, say, a type here to the associated coset, right, of G mod G00. So remember, this is maybe just some collection of intersection of formulas, right? And so each type P is going to live inside one of the cosets. And the point is that this is going to be an isomorphism when restricted to the ideal group. Right? So this is maybe, I mean, this is how the theorem goes. This isn't really a proof of the theorem, but okay. So, okay, so this is somehow the maybe, how should I say? This is somehow the important connection, at least, okay, up to maybe a couple years ago, right? And okay, since then, right, there's been somehow a lot of nice work. Okay, I mean, maybe what should I say? There's many somehow open directions, even coming out of this, right? So one question that I'm really kind of interested in is, say, somehow dynamics, say, involving the space of invariant types, right? So all throughout my entire talk, excuse me, we've been thinking about the space of, say, global finally satisfiable types. But somehow, much of this work, much of the theoretical work can be done in the space of invariant types, but it's very unclear what's going on. Like actual, like the dynamical system in this setting, what is the Newelski product doing? What are the relations between the finitely satisfiable space and the invariant space? It's something that I'd really like to know more about. Yeah. Maybe another somehow open direction that's very close to me is thinking about maybe something called like convolution dynamics, right? So this whole setup works in the measure case. So there's a random variance where instead of working with points, right, with types, you can do everything with Keyser measures, right? You can replace points with measures. And understanding these dynamical systems, okay, in the NIP setting, they're kind of known, but outside of definably amenable NIP, almost nothing is known. So it would be very, very nice to understand maybe what's going on in this setting. Maybe also, so in the measure setting, you can also look at, say, groups acting on the space of measures. And it turns out that if I'm in NIP, nothing new. But if you leave the world of NIP, I don't think anything is new. Right? There's many, many questions, maybe in this direction. And somehow, the last thing that I think is quite important and maybe hasn't really been developed is somehow property T. So property T is somehow an orthogonal property to amenability, and in practice you can prove things about property T, right? Groups that have property T. And it turns out that if I take an amenable group and a group that has property T, if a group has both, then it's compact, right? So somehow it's somehow an orthogonal property that I think in the model theoretic literature hasn't really been explored. And I think there could be maybe some very nice avenues there. Okay. And okay, that's the story that I wanted to tell. Thank you very much for coming to my talk. Thank you.
Okay, thank you. Thank you for the nice talk. Any question from audience?
Well, I'm sorry, I have two general questions. Thank you very much. Dear Kili, well, you will be remarkable report. Question number one. You have mentioned Hausdorff semi-groups. Why is it so well, they're remarkable for you, and why you will be taken in use, and mentioned this several times in your report? This is the first question.
So the question is why I like left continuous compact Hausdorff semigroups?
Yes, Hausdorff semigroup will be. Is it so very important for your will be scientific direction? Yes, or it's.
So I think so compact Hausdorff is just referring to the topology on my underlying thing, right? My underlying set, yeah. And for me, it's very, very important. So the important thing, two important things maybe. So yes. Number one, the space that I care a lot, the space that I care a lot about, so maybe this space, is a compact Hausdorff semigroup, yeah. And this is a space that somehow is, right, if I look at a space of types, it's always going to be Hausdorff, and it's, okay, if it's a closed subset of space of types, it's always going to be compact, you know? And kind of, really, the thing that I care about is maybe these objects. And if I have this weird Newelski product, then it's always going to be it's always going to have this left continuous operation. So it shows up somehow very naturally, maybe in model theory. And okay, I mean, these somehow, so why did these come up in the first place? These left continuous compact Hausdorff semigroups. Well, they come up because, I mean, they are more or less these excuse me, they're these Ellis semigroups, right? If I just take a group action, you know, some dynamical system, and then take its compactification, you get one of these left continuous compact Hausdorff semigroups.
Well, okay, and the second question, thank you. The second question is, will be in physics will be the theory of elementary particles. The theory group is the special place, yes, and for not only for the explanations of some will be phenomena like transformation of energy into the mass. And the theory of group will be a remarkable place for there. So general question will be your scientific direction can somehow, maybe later on, some will be part of your research might be, whether or not it might be applied to the some will be, this will be very, very definite will be parts of will be fundamental sciences like physics.
Ooh. Ooh. I think, for me, so these objects, so these objects here, right? These somehow these compactifications of dynamical systems. I think for me, it's very hard. Okay, maybe. So I think, okay, I have some answer actually. Okay, so I want to look at this example just for a second. Yeah. So if I'm thinking about things that look like the circle, so somehow some geometric things, right? In model theory, sometimes when you start with an object, you want to do this thing where you blow it up and you make it really big. Yeah. So that's somehow what's going on here. But then when you do this all this construction and do this quotient, you get back your original thing. And somehow, like what's actually going on is you're doing something like adding infinitesimals, and then this is showing that you can forget about them, right? So what do I mean? I mean that if there is connection to say like natural sciences, somehow it's about like adding infinitesimals and being able to figure out that you can get rid of them. Yeah, something like this. So adding infinitesimal distances and then being like, oh, it didn't actually matter that I added them. But other than that, like, I mean, yeah, I mean, I think it's very interesting, but I think somehow very difficult. Yeah, very difficult to
very difficult. Yes,
yeah, very difficult.
Thank you so much.
Thank you for the question.
Any other question? Okay, Kyle, I have one general questions. In this dynamics and the semi-group theory, you consider this minimal left ideals. How about the maximal one? In just like, is there an alternative or something which is similar to that ones?
Well, I think if you take the maximal, you just get the whole space, right? Something like this. But I think so. There's a lot of things that I don't know about maybe other ideals living in the space. So I think that's a good question. I don't know, like really, I know things about the minimal left ideals because of this old theorem that essentially tells you what they look like, right? They look like this. They look like they really are kind of like a kernel, right? So they somehow they can really just be broken up into groups that are all isomorphic, right? They're all the same group, and they're somehow they fit together. But I think there's many open questions about like what this thing actually looks like topologically. Like there's another topology that you can use, and okay, I mean there's many questions on how things actually look. But other ideals, yeah, I think people know much about the minimal ones just because there's this decomposition theorem. And I think the other ones are much more difficult to deal with in general.
I see.
Yeah, I know less. Yeah.
Okay. Thank you. Any other question? Okay. So if no question, then let us thank again for the speakers for the nice talk. Thank you, Kyle.
Thank you. Thank you for letting me speak.
Okay, so we have now 5 minutes to prepare for the next talk. All right. Thank you again. So let's welcome our next speakers, Tatyana Zambarnaya from Institute of Mathematics and Mathematical Modeling, Almaty, Kazakhstan. So Tatyana, please.
Thank you. So thank you for inviting me to give a talk here, and happy Logics Days to everyone. I will talk about some concepts relating with the countable spectrum of theories of a first-order theories, and especially with a definable linear order. And many results will be concerning the maximal case. So the spectrum problem is to describe such a function, the function IT lambda. It is the number of non-isomorphic models of a theory T of cardinality lambda. For countable theories and uncountable cardinalities lambda, the spectrum problem has been completely described by Hart, Hrushevsky, and Laskovsky. And for the countable case, Watts proved that the number of countable non-isomorphic models cannot be equal to 2. Ehrenfeucht gave examples of theories with a finite number of countable models starting from 3. And Morley showed that if such a number is infinite, then it has only 3 possibilities. So it can be either Aleph 0 countable, Aleph 1, or 2 to the power of Aleph 0, so continuum. And this is, of course, if continuum hypothesis fails. And the question of whether it can actually be equal to Aleph 1 is called the Watts conjecture. So it supposes that there is no complete first-order theory T of a countable language, such that the theory has more than countable and less than continuum number of countable non-isomorphic models. Watts conjecture has been confirmed for various classes of theories. So, for example, theories on this slide. And here are the classes of theories with a definable linear order for which the conjecture was confirmed. And the question here is whether it is realistic to prove Watts conjecture for linearly ordered theories, but without any other additional restrictions. For example, according to Teitzlin, every structure is bi-interpretable with a lattice. And from this, it follows that Watts conjecture is equivalent to Watts conjecture for lattices, so for partial orders. And next, we will look at total orders. So let M be a structure with universe M and signature sigma, and take any element A1 from M and replace A1 with a countable dense subset of the set of rational numbers. Take a distinct element A2, do the same thing for it, and make the sets, so the blue and red elements, make them mutually dense. So we can do this for all the elements of the model and construct a new structure, so M star, to have the universe to be all of those such colored elements, the initial language, so signature sigma, with 2 new binary relations. So the standard relation of linear order on the rational numbers and the equivalence relation, which will just define those classes generated by the same element from the initial structure M. So if, for example, sigma is relational, to interpret relation R from sigma, so to say that M star R holds on some elements B1, B2, Bn, if and only if on the initial structure M, the same relation holds on the generators of those elements. So for example, if in M, the relation R holds on A1, A2, then in the new structure M star, it will hold on any pair where the first element is red and the second one is blue, but the order here doesn't matter. And so such an order is fictitious, and it basically gives no useful information about the structure itself. So by Ehrenfeucht-Freysse game, we showed that if n is a countable model of the theory of M. So if n is elementary equivalent to M, then n star is elementary equivalent to M star. So such a construction preserves theory of the model. And the function, so the transition from M to M star is a bijection between the classes of countable models of theories of M and M star. So cardinalities of those classes are the same, and we get this theorem. So M is a countable structure of a countable signature. Then there should always exist a countable linearly ordered structure M star, such that theories of M and M star have the same number of countable pairwise non-isomorphic models. And this implies that if there exists a theory T of a countable language, which contradicts Watt's conjecture, so which has Aleph-1 non-isomorphic models, then there should be a linearly ordered theory, T star, which also contradicts Watt's conjecture. So this means that, yes, we can restrict to linear orders in general, but there is no advantage in doing this, because studying linear orders is the same as studying like the general class of theories. What largely affects the number of models is in how many ways we can realize a type and the relations between the types themselves. Examples of such relations are the relation of weak and almost orthogonality of types. So let A be some subset of a model, P and Q be one types over the set A. And in general, those definitions are given for n types, but for linear orders, we look at one types. And types P and Q are weakly orthogonal if the union P of X union Q of Y is a complete two type. So this union is not divided by any formula and its negation. And equivalently, we can say that P is not weakly orthogonal to Q if there exists such an formula phi of xy, where each or equivalently some realization alpha from P, the set phi m alpha divides the set of realizations of Q. And if there exists such a formula phi, which is a proper subset of Q of M, this case is said to be P is not almost orthogonal to Q. So on pictures, in general case without the linear order, so we have types P and Q. Each type is defined by intersection of definable sets from this type. And realizing P by some element alpha, if P is not weakly orthogonal to Q, then the set phi m alpha will look something like that. So it will split the type Q of M. And if the types are not almost orthogonal, then this set will be a proper subset of Q of M. So what we have here is if, for example, some model realizes the type P, like by element A, then the set phi m alpha should always be a subset of Q, and this type Q should also be realized in this model. So in this way, the relation of not orthogonality forces types to be realized, and relation of orthogonality allows them to be realized and emitted separately from each other. So it affects the number of countable models. And a great example of using this property is Kulbeshev's paper on Watt's conjecture for weakly minimal theories of finite convexity rank. So first of all, such theories are binary. I will talk about this later. And so binarity allows us not to look further than two formulas. And knowing kind of each type and relations between of those types, so orthogonality between those types, it allows us to count the number of countable models. And weakly minimal theories have some really nice properties, so types and relations of those types. and we will look at those later. Now, we consider the standard notion of convexity of a set, and we say that a formula phi of xy is a convex formula if it defines a convex set in every model and for every parameters b from this model. Next, on linearly ordered structures, there is a concept of a convex closure of a formula phi. So it is a formula phi c, which defines the smallest convex set containing the set definable by phi. And a convex closure of a type, so for type P, it's the type PC. It's the set of all convex closures of all formulas from the type P. So the type P is complete, but the convex closure of PC is not necessarily complete. So for example, here on this picture, we have three complete types, which are kind of mutually dense with each other, and they have the same convex closure PC, like represented by those arrows. So in general, there can be one finite or even infinite number of types with the same convex closure. But for example, for weakly minimal theories, each type is the same, so coincides with its convex closure, and each type itself is convex. So maybe I will draw this. So weakly minimal theories are theories where each definable with parameter, each definable with parameter set is a union of a finitely many convex sets. So for example, like this. And if a formula defines a finite number of such classes, then each of them, so the first, second, and third, will in turn be definable by a formula. And then for a formula to be inside of the type, so only one of them can be inside of a type. So each type should be inside of here, so inside of intersection of convex sets. So each type is convex and it has convex closure equal to itself. And now we'll define the notion of orthogonality for those convex closures of types. So we say that a formula phi monotonically increases or decreases on a set B if its left and right borders monotonically increase or decrease. So for all B1, B2 from B, with B1 less than B2, we have that the left border of the set phi MB1 is smaller than the left border of phi B2, and the same for the right borders. Okay, and now we can define the convex weak orthogonal, so not convex weak orthogonality of types PC and QC. So we say that PC is not convex weakly orthogonal to QC if there exists an A-definable convex monotonic on PC of M formula, which has the same property as in the general definition of non-weak orthogonality, so that the formula phi and its negation splits the set QC of M for each realization from PC of M. And if this set phi is a proper subset of the set QC of M, then we say that PC is not convex almost orthogonal to QC. So this is analogical to the non-almost orthogonality. Okay, and yeah, for linear orders, it just means that phi is bounded by some elements, gamma 1, gamma 2 realizations of QC. So here are some relations between the weak and almost and convex orthogonalities. So for example, first one, non-weak orthogonality is symmetric. non-almost orthogonality and not convex almost orthogonality implies weak and not convex weak orthogonality. And fourth and fifth say that if convex closures of PC and QC are not convex weak or not convex almost orthogonal, then each type P0 with the closure PC will be non-weak or non-almost orthogonal for either each or for some Q0 with the closure QC. And such relations of convex orthogonality preserve some nice properties of types. So, for example, the closure PC is said to be quasi-rational to the right or to the left if the right border or left border of the set of realizations of this type is definable by some A formula. And so for linearly ordered theories and types P and Q over some set A, one types, if PC is not convex weakly orthogonal to the closure QC, then PC is quasi-rational if and only if QC is quasi-rational. So this property is preserved. And another property which the orthogonality preserves is definability of types. So type P is definable if for each formula phi, there is a formula d phi, which checks whether phi of xb for tuple B of parameters belongs to P if and only if the formula d phi holds on this element D, on this tuple B. So in general, the non-weak orthogonality does not preserve this notion of definability and as well as isolation of types. But the convex non-convex weak orthogonality preserves this notion. So if in a linearly ordered theory, P and Q are non-algebraic one types with PC not convex weakly orthogonal to QC, then definability of P implies definability of QC. And the last property of such orthogonality is that if P and Q are non-principal one types with their closures being not convex weakly orthogonal, then this basically this relation is symmetrical as well. So PC not convex weakly orthogonal to QC, if and only if QC not convex weakly orthogonal to PC. So this was for the relations between types. And now we look at what is happening on the sets of realizations of types. So let P be a non-algebraic one type over a set. And there is a notion of a P preserving and convex to the right and convex to the left formulas. So it's a formula phi of xy with special properties, which I'll just show in pictures. So we have a type P, and the formula phi of xy is said to be P preserving, so P for the type P. If for each realization alpha of the type P, the set phi m alpha is located strictly inside of the closure of P. So it is bounded by some realizations gamma 1 and gamma 2 from P. And next, if such a set is convex and alpha is its left endpoint, then phi is called to be convex to the right. And if alpha is here, so the right endpoint of this set, then it's called to be a convex to the left formula. And now we can take another convex to the right formula psi, and let us denote by CRFP to be the family of all such P preserving convex to the right formulas, and the same CLF for convex to the left. Then on the set of such formulas, there is a natural relation of linear order just by set inclusion. So on this picture, psi contains phi, so psi is greater than phi. And what can also be done here is we take a realization beta of the type and look at how the formula phi behaves on this element beta related to phi of a. Sorry, alpha. And the first type is for phi of m beta to be inside of phi of m alpha, or for them to have the same right border, or for it to jump forward. So the first case is the least studied of them all. Those are kind of like arc formulas, and such type of formulas was used by Omarov in his paper. So here he constructed an example of theory which had a countable number of countable models with its constant expansion having finite number of models. And he also tried to answer this question, so question by Taimanov, of whether there is a theory T which has continuum many countable models and its constant expansion having either countable or finite number of models. And so in the paper 2, authors proved that Taimanov's question is still open. But quite recently, Kudybergenov proposed that he answered Taimanov's question, and his paper is accepted to a journal, but we're waiting for it to be published. Okay. The second case is when phi m alpha and phi m beta have the same right border. So this is called to be an equivalence generating formula. And so for those formulas, we can take the family of all elements which have the same right border by phi, and this will be an equivalence class. Such formulas were studied, for example, by Kulpeshov. So he proved that in weakly minimal theories with non-maximal number of countable models, for each non-algebraic one type over the empty set, every p-preserving convex to the right or convex to the left formula should be of this exact kind, so equivalence generating. Here is a long restriction. So this is a case when a theory has maximal number of countable models. So T is linearly ordered and satisfies first three cases. So first one says that there is no special kind of a uniformly definable equivalence relation E. Second one is that the set of types with the same convex closure should always be finite. So for example, it is always one for weakly minimal theories. And the third one, that all p-preserving convex to the right and to the left formulas should be of this second kind, so should be equivalence generating. And if a countable linearly ordered theory satisfies this restriction, and it has a type P with CRFP, so the family of all convex to the right formulas on P, set being infinite, then this theory has the maximal countable spectrum. And the last type of formulas is the quasi-successor formula. So this is when this set, so phi mb minus phi ma is non-empty. And so what can be done here is we can look at all the elements from the type which are reachable in terms of phi from alpha. And this will be like a neighborhood of the element alpha. And what is nice here is that those neighborhoods, so if you have like a neighborhood of alpha 1 and alpha 2, then here, so here in between of them, it will be a non-isolated type over alpha 1 and alpha 2. And so we can arrange those neighborhoods in any order type, so discretely, densely, and etc., etc. And this property of here being a non-isolated types allows us to do this and to get continue many possible orderings. Okay. And so here's the theorem for quasi-successor formulas. So T is an ordered theory with a type P, non-algebraic, which has an A-definable quasi-successor formula on it. Then countable spectrum of such theories should be maximal. And another property of formulas on linear orders is each formula has such a convex equivalence relation. So for a formula theta, it's a relation E theta. And so on picture, it defines largest convex subsets of the set theta. So here we have three convex subsets. And there is, of course, a linear ordering on the set of such classes. And they can also be, this ordering can also be dense, discrete, finite, or infinite. And here we have the theorem that if in a linearly ordered small theory, so small means non-maximal number of types, theta, so not, yes, so small means that the set of 1 types or n types should always be countable for each n. And theta is one formula such that for each natural number n, there always exists a number mn greater or equal than n, and a discretely ordered chain of convex E theta classes of length exactly mn. Then it implies maximality of the number of countable models of such a theory. And also by compactness, if there exist infinitely large discrete chains, then there should be just infinite. So existence of finite infinitely large discrete chains implies existence of an infinite discrete chains of such convex classes. Okay, and it implies maximum number of models. Next property is the property of n-arity of theories. So a theory is said to be n-ary if every its formula is equivalent to a Boolean combination of formulas with maximum n free variables. And if n is equal to 2, this theory is called binary. So for example, here are some papers concerning binary theories. So in the first paper, Kulpeshev and Sedoplatov, while proving Bott's conjecture for quasi-minimal theories, they showed that if such a theory has a non-maximal number of countable models, then this theory should always be binary. Second one, similarly, Kulpeshev showed Bott's conjecture for weakly minimal theories of finite convexity rank, and showed that if such a theory has non-maximal number of countable models, then it should be also binary. Next, in the third one, Makoni and Atanovich proved Bott's conjecture for binary stationarily ordered theories. And in the fourth one, Kulpeshev introduced notion of a binary one type in ordered theories. And he proved that Aleph zero categorical weakly minimal theory is binary if and only if every non-algebraic one type over an empty set is binary. And next we introduce a notion of an n-ary M type for arbitrary theories. So first says that an M formula is n-ary if it is equivalent to a Boolean combination of n formulas. And taking into account this definition, a theory T will be n-ary if every its formula is n-ary. And we'll say that an M-type P is n-ary if P is a unique extension of such a set to a complete M-type. So of the set of all n types, which are subtypes of P, to a complete M type over an empty set. So in other words, this is a type which is uniquely determined by n types. And for a complete series in countable signatures, let n be a natural number starting from 2. Then the theory T is n-ary if and only if for each m greater than n and each m type p, this type should also be n-ary. And so an easy corollary from here is that in n-ary theories, the number of types is determined by the number of n types. So for example, a theory T is small if and only if the set, so an n-ary theory is small if and only if the set of n types, S and T, is either finite or countable. And if S and T is finite, then for each m greater than n, SMT should also be finite. Another property of types is extreme triviality of them. So let T be a small complete theory, P be a non-principal type, over here A should be finite over a finite subset of some model, and let A be some enumeration of the set A. Then the type P is said to be extremely trivial if for every natural number n and for every n realizations, so the tuples B1, beta 1, beta 2, beta n of P, the following holds. So this is the prime model. So in the prime model, M over those tuples B1, beta 1, beta 2, beta n, and the tuple over which the type is defined. In this prime model, nothing is added to the realization of the type P other than those realization beta 1, beta 2, and beta n. So the most basic example here would be just taking a family of nested sets or nested unary predicates, PIs. So, and such that each layer here, so each layer between PIs and PI plus 1 should have an infinite number of elements. And then we can take the type P to be the set of all PIs, all such predicates. So it's here. And this type is extremely trivial just because of the scarcity of the language. So for example, we can realize it by one element, and this element will not force anything else to be realized in the prime model over this element. So analogically, we can have 2 realizations, 3, 4, and etc., and also finite, any finite and countable number of realizations. So such a theory has a countable number of non-isomorphic models. And also, there are different kinds of extremely trivial types. I think they're called almost extremely trivial. So it's when, for example, each element has its pair. So there is another binary relation, and each element is paired inside of the model. Then realization of one element will force another one to be realized, but nothing apart from it. So this case will also have a countable number of countable models. And a linearly ordered example of such trivial types is taking the standard dense linear order without endpoints and a countable family of unary predicates PIs, which are dense, codense, disjoint. And so imagine it like a linear order where there is an infinite number of colors. All of them are mutually dense. And then we can take the type P to be negation of all of those PIs, all of those colors. So this type will be also extremely trivial. And by the next theorem, this theory has continuum many countable non-isomorphic models. So theorem is the following. So T is a countable linearly ordered theory. And if there exists a finite subset A of some model and a non-principal extremely trivial type P over this subset, then countable spectrum of such theories should be maximal. And I want to finish on some theorem not necessary for linear orders for the general case. So there is a notion of a finite diagram of a model given by Shela, and later John Baldwin called it as also a dowry, and he gave a notion of a dowry of a set, not only a model. So a finite diagram of a model M is the collection of types P which are realized in the model M. And the following theorem is that if T is a complete countable theory with alpha countable models, so a theory which contradicts Watt's conjecture, then there should always exist a family of alpha countable models of the theory T, which all have the same dowry, so the same finite diagram. And so for each theory which contradicts Watt's conjecture, there should always be alpha models, all of which have the same number of, the exact same types to be realized and the exact same types to be omitted. Okay, so I think I'm quite ahead of time, but this is everything I wanted to tell about. So thank you. And do you have any questions? Yeah.
Thank you, Tatyana. Question.
I have a question. So do you think Watt's conjecture is true, or do you think it's false?
I think it might be true. So because of all of those classes of theories for which it is true, and probably I shall talk about our plans for the future. So here, all of the theorems were, most of them were for the maximal case of the number of countable models. And what we plan to do next is to combine all of the cases of maximality, so take their negation and probably get some properties for non-maximal case and maybe show Watt's conjecture for those classes. So I think it might be true. Yeah.
Thank you.
Thank you.
Any other question? Yes, please. We cannot hear you. The mic, Sandbek Mirza, please, the microphone is mute.
I'm sorry, yes. Thank you very much, Tatyana, for your very present, well-being scientific report. Well, I have not so much questions, but only two. What do you mean linearly ordered theory? Can you present any example of such theories?
Yeah, so it's any theory with the linear order in its language, or for example, where linear order is definable.
Like
so,
this.
Yeah, so any of the classes from here are linear. So we mean just a theory with the property of linear order in the language.
Mm-hmm. Then the next question will be weakly orthogonal will be systems. The system or two elements might be orthogonal or not. But what do you mean by weakly orthogonal? Huh?
Yeah, so where is it?
Yes.
So yes, there is a notion also of a system of types to be weakly orthogonal. So the general definition are P and Q are weakly orthogonal if P union Q is a complete type. So what also we can look at is, for example, a family, even an infinite family of types with this property. So for example, so in general, this one is, okay. So this is Sn, and the types are with tuples of length n. And so as we consider one types for linearly ordered theories, and in general case, there are n types. And we can have, for example, a countable family of types where union of any of those is a complete type, and taking any of the types not from the family, they also do not affect realization or omission of this given countable family. And this is a good example because when you have a countable many types, each one of them can be realized or omitted independently from each other if you have such an orthogonal family. And then there is a countable number of them and continue many ways for to realize and omit types. So then the theory will have maximal number of countable models.
Okay, thank you very much, Tatyana.
Thank you.
Yes, thank you. Thank you.
Any other question? We need more question to Tatyana because we have more time. So
Yeah.
we welcome more question. Okay, if no question.
I have another question.
Yeah, sure, please.
I think it might be a little technical. But okay, at some point, I have written non-weakly orthogonal does not something definable types does not non-weakly orthogonal does not preserve definable types, something like this.
Yeah, so the general non-weak orthogonality does not preserve it. Yeah.
So what? Oh, sorry. Oh, you're on the exact page.
Oh, sorry.
But I guess my question is, so what, I mean, but are other properties preserved by non-weak orthogonal? I mean, what is anything preserved?
So non-weak orthogonality, the general case, does not preserve definability of the types, but the relation of non-convex weak orthogonality, so non-orthogonality of convex closures of types, preserves it. And so the properties are definability, quasi-rationality, and from quasi-rationality, it follows that if one convex type is isolated, then the second one should also be isolated. So far we only have those properties.
So so there's this notion of like generic stability for like a type that was defined by like Pillay and Tanovich, but I don't think like if you have a linear order round, I don't think you're going to have any. But I guess my question would be like if generic stability is preserved by like I guess it can't. Well, I don't know. I mean, I don't know, but I don't know if there's actually like theories in which these types live that in which this is a good to check. But okay, thank you.
Yeah, thank you.
Okay, thanks for the question. Any other? No question. Then thanks again for the speakers for nice talk. Thank you, Tatyana.
Thank you.
Thank you.
So we continue our workshop, and our last speaker for today is Paul Shafer from University of Leeds, UK. Okay, Paul, so the floor is yours.
Thanks so much. Thanks, Manat and Nikolai, for having me. It's really great to be part of World Logic Day. So I'm sorry, this isn't really about model theory, this talk. This is much more about computability. The idea here is to just explore effective versions of ultra power and ultra product constructions. So that's what we'll talk about. Okay. So I've got sort of two groups of collaborators here before I get too deep into it. One's with a lot of people: Ruben Dimitrov, Valentina Arizanov, Andrei Morozov, Alexandra Saskova, and Stefan Vatev. So this group plus me, I'll denote by this sequence of symbols. And then my other collaborator, which I'll talk about near the end, hopefully, is David Gonzalez. Okay, so what we're going to do here is build ultra product and ultra power like structures for computable structures, and instead of using an full-blown ultra filter, we're going to use what's called a cohesive set. So let me remind you what that means. So I've got a countable sequence of subsets of the natural numbers, which is the sequence A here at the top. And for any such thing, I can find any such sequence of A's. I can find an infinite set C, such that for every one of my A's, either C is almost contained in that A or almost contained in the complement of that A. So the subset with a little star here means almost containment or eventual containment except for a finite number of mistakes. Okay, so a C like this for my sequence A is called an A cohesive set. And then there's a few sequences of A's that we're particularly interested in. One is if I were to just list out the recursive or computable sets, then the corresponding C is called R for recursive cohesive in that case. And the situation in which I will most be interested in is when my sequence of A's here list out all of the computably recursively enumerable sets, right? And then if I have a set C that's cohesive for the RE sets, that C is just called plain old cohesive. Okay, so if I say cohesive with no other qualifiers, that means for the collection of recursively enumerable sets. Okay. Right, so the idea of what we're going to talk about arguably goes way back to Skolem and his countable non-standard model of arithmetic. So what he did was basically this, right? He started with a set that's cohesive for the collection of arithmetical sets, right? Which is perfectly good, right? Because there are countably many arithmetical sets. And then he looked at arithmetically definable functions on the natural numbers, and he defined these relations here, right? We'll say that f and g are equal up to the cohesive set if, well, the cohesive set is almost contained in the collections of n's for which f of n equals g of n, or maybe more simply said that f of n equals g of n almost everywhere on the cohesive set. Right, and likewise we can say that f is less than g if f is less than g almost everywhere on the cohesive set. Right, and then similarly define plus and times pointwise. Okay, right. So the cohesive set, or maybe rather you could think of the like supersets of the cohesive set, are sort of playing the role of the ultra filter in this situation, right? So f and g being equal almost everywhere on the cohesive set is like saying that the collection of n's for which f of n equals g of n is in the ultra filter. Okay, so with these definitions, we could make a ultra power like structure where we look at the equivalence classes of these functions up to this equality here. Okay, right, so if we do that, then the less than respects these equivalence classes here, and likewise so do plus and times. So we get this structure made out of these equivalence classes, right? It's a countable structure because there were only countably many arithmetical functions. You can prove that this thing models true arithmetic by sort of the same way you prove Wash's theorem for ultra powers. Okay, and then you can check that this is a non-standard. It's going to be a non-standard model of arithmetic, right? And the standard elements in this model are going to be the elements represented by constant f's and g's, and then the non-standard part is everything else. And then, for example, the identity function represents a non-standard element. Okay, so this was Skolom's idea, ultra-power-like construction for constructing a countable non-standard model of arithmetic. Okay, and then people had some questions about this. So there was some sort of sporadically work in this direction, still focused on models of arithmetic for some time. For example, Tenenbaum asked, well, what if we did like Skolom's construction, but instead of arithmetical functions and a set that's cohesive for the arithmetical sets, we reduce everything to computable, right? We only want to look at recursive functions, sort of representing the points instead of arithmetical functions. And we only want to assume that our cohesive set is cohesive just for the computable sets, right? Can we still come out with a model of arithmetic? Okay, and it turns out you can't even get models of PA this way, and it fails sort of immediately quite badly. And there were more investigations in this direction. I think a snappy theorem here of Lerman says that, well, if I want to sort of consider constructions like this, which I'll denote this way here, right? This power construction over this structure here, right? Standard model of arithmetic via this cohesive set C here. Okay, so Lerman says, if I want to do this and I only want to consider pi1 definable cohesive sets, okay, then the result that I get, right, the powers that I get, right, they are going to be elementary equivalent if and only if the two cohesive sets are many one equivalent. Okay, so this is, I think, a nice situation where the result that you get depends exactly on some relation between the cohesive sets that you're doing the power by. Okay. Right. Okay, and then various people studied certain other sorts of effective ultra power constructions, and the focus there was still mostly on powers of the standard model of arithmetic and questions of whether or not the power that you get is rigid or totally rigid. Okay, so for example, two other ultra power like constructions are the recursive ultra powers. They're also called Nerode semi-rings. And what you do is you look at total computable functions representing the points, and then you use an ultra filter on the Boolean algebra of the computable sets to make your power. Okay, so that gives you what's called a recursive ultra power. And then you can do something a little more permissive, where you now have your points represented by partial computable functions. And to make your power, you look at maximal filter in the lattice of computably enumerable sets. Right? So this is another style of effective power. Okay, and again, there were questions of, well, is the result rigid, meaning you have no non-identity automorphism, or maybe even better, totally rigid, meaning you have no non-identity self-embedding even. Okay, so there were several results in this direction over quite a number of years. So it turns out that if you do these RE ultra powers of arithmetic, then the result is always rigid. And then much later, it was shown that if you do these recursive ultra powers, then the result is totally rigid. Okay, and then this all culminated in a much more recent result of Shavrikov, who said that, well, actually the RE ultra powers of arithmetic are totally rigid all along. Okay, so that was sort of one line of work considering effective ultra power like constructions. We are going to look at these effective powers via cohesive sets, but not just for the standard model of arithmetic, but for any kind of computable structure. Okay, so the idea to look at this was due to Dimitrov. So he says we'll have a computable structure A. So a computable structure is just structure where the domain is the natural numbers, or maybe a computable set of natural numbers in case you want to allow finite ones, and then where all the functions and relations are computable. Right. So for example, a computable linear order is one where it's computable to tell which elements are less than which other elements, or computable group is one where it's possible to compute the group relation. Okay, so so given a computable structure, we can form the cohesive power of the structure just like Skolem did. So here we're having a cohesive set. So cohesive for the computably enumerable sets, right? And then our points in the power are going to be represented by partial computable functions whose domain almost contains the cohesive set. Right, and then as before, right, we define two partial computable phi and psi to be equal up to the cohesive set like before, right? And we say that the relation holds of some representatives, these psi's, if and only if the relation holds almost always on the cohesive set. And then again, functions are computed pointwise. Okay, and we get an ultra power like structure out of the equivalence classes like before. Okay, and you can do this exact same thing for products rather than powers. If I have a uniformly computable sequence of structures all in the same language, like a computable sequence of groups or a computable sequence of linear orders, definitions are all exactly the same. I just wrote everything in terms of powers to cut down on the notation. Okay, so if you make a ultra product like construction, you might want to know how the basic things like Wash's theorem carry over. Okay, so it turns out how much of the Wash theorem you get depends on how much you know about your structure in the first place. Okay, so we say that a computable structure is n decidable if you can compute the truth of sigma n formulas with parameters, and then structure is fully decidable if you can decide the truth of any formula with parameters. Okay, so a plain old vanilla computable structure counts as a zero decidable, where you can just compute whether or not the atomic formulas are true. Okay, so the default case, plain old computable structure is the n equals 0 case of all of this. So if you have a computable structure, then the Wash theorem preserves pi2 facts about your structure going upwards. So if you have a pi2 thing that's true in your structure, then it'll be true also in the power. And then if you know more about your structure, you know more accordingly, right? So if your structure is n decidable, then this is true for pi n plus 2 formulas. Okay, in particular, if you know everything about your structure, right? If your structure is decidable, then you get the full Wash theorem in this situation. Okay, I guess I should say, so again, I phrase everything here just for powers, but this is all true for products as well. there's a special situation where you get a little more of the wash theorem, which is where you're really looking at powers, right, of a single structure and sentences, so no parameters. Okay, so here, if you have the cohesive power of a computable structure and you're just considering sentences, then this preserves sigma 3 things going upward instead of just pi 2 things going upward. So if I have a sigma 3 thing that's true in my original structure, it'll be also true in the power. Okay, and then likewise, if your structure is more decidable, then you get more. So if you have n decidable instead of just 0 decidable, this will preserve sigma n plus 3 things going upward. Okay, right, and then we'll maybe see some examples later on where in particular this one is tight, right? You preserve n plus 2 things going upward, but not better than that in general. Okay, and you also get a little saturation with these cohesive powers and products. So I think yeah, everything on this slide is true for both powers and products. What we care about here is a structure being recursively saturated, right? Meaning that it realizes every computable recursive type, right? Meaning you have a program that tells you whether or not your formula is in your type or not. Okay, and then also what's called sigma n recursively saturated, which means same thing, except for you are not considering types of any old formulas, just at most sigma n formulas. Okay, so if you have a fully decidable structure, then the cohesive powers are going to be fully recursively saturated. Okay. If not, then you only get a little bit of saturation, right? If you know that your structure is n decidable for n at least 1, then you're going to be sigma n recursively saturated. Okay. And then I guess the main point here is maybe these last 2 bullets, or maybe this last bullet, which is to say that, if you know something about your structure, but you also know something about your cohesive set. So these first items are for any old cohesive set, right? But if your cohesive set is not too complicated, right? Delta 2, computable from 0 jump, for example, then you get a little more saturation. Okay, so if you have an n decidable structure by a delta 2, power by a delta 2 cohesive set, then the result is sigma n plus 1 recursively saturated. Okay, and also you have the n equals 0 case. Okay. Right, so if you do a cohesive power of a computable structure by a delta 2 cohesive set, right, then you get a sigma 1 recursively saturated result. I should have maybe said up front. So part of the point of this project is to sort of tease out what's similar and what's different between the classical ultra power situation and these more effective ultra powers, right? And well, part of these having a more like effective ultra power like construction, there's one way that's more effective is that we're looking at not just an arbitrary structure, but a computable structure, right? And then we're building these structures out of, not arbitrary functions, but I guess in this case, partial computable functions. Okay, but then there's also the effectivity of the cohesive set that we're using to take the power as well, right? So if we want things to be as effective as possible, it makes sense to consider also restricted complexity on the cohesive sets. And for us, that means pi 1, or more generally, pi 2 cohesive sets. Okay, so some things that I'm going to say are going to be just for any cohesive set in general, but then we'll have stronger things if we have if we assume some more effectivity on the cohesive set itself, in particular that the cohesive set is delta 2. Okay, so some things are going to be, for every delta 2 cohesive set, blah, blah, blah. Okay, so those are sort of, the basic facts about these cohesive power style constructions, right? How just in general, how much of Wash's theorem gets preserved and how much saturation do you get? And now I kind of like to frame what we investigated as kind of a dual to what Lerman did. So if you remember this result of Lerman that I hinted about earlier, right? You can think about what he did as, well, he fixed a computable copy, right? Computable presentation of a computably presentable structure. By presentation here, I just mean, an encoding of your structure over the natural numbers, right? Not like presentation in the sense of a presentation of a finally presented group or something like that, right? Just of a isomorphic copy of your structure where the domain is the natural numbers or a subset thereof. Okay, so fix a computable copy, computable presentation of some computably presented structure, right? For Lerman, that was the standard model of arithmetic. And he varies the cohesive set and sees what powers he gets with this fixed structure and the different cohesive sets. And what he discovered is that, well, if you restrict to the world of pi1 definable cohesive sets, then the powers are going to be elementary equivalent, right? If and only if the two cohesive sets were, many one equivalent in the sense of computability theory. Okay, right, so we want to do something kind of dual to that, right? We'll, instead of fixing a structure, we'll fix a cohesive set, okay? And we'll fix a particular structure, but we'll vary the computable presentations of that structure, okay? So the main thing I want to look at is just the natural numbers, omega, as a linear order, but the different sort of computable ways to present that structure. And then seeing that, well, as we vary the presentation, can we get different structures arising as the powers? Okay, and again, this will highlight some differences between these effective cohesive power type constructions and the classical ultra power construction. Okay. Right, so I want to look at linear orders instead of arithmetic for the following reason, right? So classically, right, if I have two isomorphic structures and I want to take, just a classical ultra power of those two structures by some fixed ultra filter, right, then the isomorphism between those two structures is going to induce an isomorphism between the powers, right? So isomorphic structures can have isomorphic ultra powers by the same ultra filter. In the effective world, right, the same thing is true if the two structures are isomorphic via a computable isomorphism. Okay, but it could be that you have two computable copies of the same structure that are classically isomorphic, but not isomorphic via a computable isomorphism, and then different things can happen. Okay, so we need to look at some structures that are like this, right? Have presentations that are classically but not computably isomorphic. Okay, so arithmetic is not like that, right? There's only if you have any two computable copies of arithmetic, they're isomorphic via a computable isomorphism. Okay, but there's linear orders, in particular, just the linear order on the natural numbers, where you can have computable copies that are not computably isomorphic. Okay, so we move the setting from arithmetic to linear orders, right? for that reason, and also because there's lots of names of linear orders. Right, so I'll use this notation, omega for the order type of the natural numbers, zeta for the integers, and eta for the rationals. Okay, and then because of the arithmetic on linear orders, you can generate lots and lots of other names. Okay, so star here means the reverse, so this will be the order type of the negative integers, for example, and then sum and product of linear orders. So this is a particularly important one, right? Omega plus dense copies of the integers, right? The order type of countable non-standard models of arithmetic. This will show up a few times. Okay, so that's one reason that we want to look at linear orders, right? Yeah, and also because there's a bunch of them that we could name. So we'll be able to say, right, not only is this power not the same as that power, but this power is this particular structure that we already have a name for, which is a little bit more difficult in the world of arithmetic, I think. Okay. Right. Okay, so we want to just explore what happens with these cohesive powers for powers of computable linear orders, in particular powers of various copies of just the natural numbers as a linear order. Again, to see some differences between this situation and the classical situation. So one thing that helps is that the powers respect the operations on orders, right? If I have the power of a sum, that the result is the sum of the powers, and likewise for products, and even more generalized products, and likewise for the reverse order. Okay. Right. And then if you take the usual presentation of the natural numbers as a linear order, right? So what distinguishes this is sort of the special one where you can compute the successor function. Okay, so if you take the cohesive power of this particular presentation of omega as a linear order, right, what you get is what you might expect, which is this order here, right? Omega plus like the naturals plus dense copies of the integers. Right, and you would probably guess this because this is the order type of countable non-standard models of PA. Right, so if you're going to guess one, this is what you're going to guess, and that is indeed what you get. Okay. Nevertheless, right, there are computable copies of omega that are not that are classically but not computably isomorphic to the usual one here, yet still have the property that they always give you this omega plus zeta eta order type when you do the power by any cohesive set. All right. So sort of a basic question is, can you get anything else other than this omega plus zeta eta order? And the point of the previous slide was partly that, well, if you want to get something else, you have to do something more than just make the successor function not computable, or make the order not computably isomorphic to the usual presentation. Okay. Right. Nevertheless, this is possible, right? For every cohesive set, you can compute a copy of omega, right? Necessarily not recursively isomorphic to the usual copy, such that the power is not isomorphic, even not elementary equivalent to this omega plus zeta eta order. Okay, and in fact, the way that what we do is make it so that the element represented by the identity function here has no immediate successor. Okay, so in this order, in the power here, there'll be an element that doesn't have an immediate successor, right? Whereas here, everybody does have an immediate successor. Okay, so and that also gives an example of tightness for one of the versions of the Wash theorem from earlier. Okay, so I have a little hint of how to do this, but maybe I'll just skip the more technical slide here. In interest of time, right? Okay. Right. So I've given talks about this a few times, and something that people tend to ask me about is the Kiesler-Schaller theorem, which states that two structures are elementary equivalent if and only if they have isomorphic ultrapowers. Okay, so more specifically, right, if I've got two structures, A and B, then they are elementary equivalent if and only if you can come up with an ultrafilter over some index set of the appropriate size, such that the ultra powers of A and B via that ultrafilter U are isomorphic. Okay, so what about this situation for the computable or decidable structures and cohesive powers? Okay, so for decidable structures, so remember that means your structure is not only computable, but you can also compute the truth of any formula with parameters. So if you have decidable structures, A and B, then this is true, right? Decidable structures are going to be elementary equivalent if and only if the cohesive powers are isomorphic for every cohesive set. Okay. Right, but if your structures are not decidable, then this breaks in all kinds of ways. All right. One of the theorems before said that if you have a cohesive set C, then you could come up with a computable copy of omega where the element represented by the identity does not have an immediate successor in the power, right? That's how we got something that we knew wasn't omega plus zeta eta. Okay, but in fact, you only need two L's, right? Just an L for if your cohesive set is eventually contained in the evens, and an L for if your cohesive set is eventually contained in the odds. Okay, so there are two computable copies of omega, which I'm calling L even and L odd, having the property here, right? If your cohesive set were contained in the evens, then the identity doesn't have an immediate successor in the power, and the other one is the same for the odds, right? And then, well, if you have a cohesive set, it's either eventually contained in the evens or eventually contained in the odds. So just for any cohesive set, one of these two structures does the job. Okay, so well, let's think about what happens if we are to just then add these two orders together and consider sort of the standard presentation of omega plus omega, right? So natural numbers plus the natural numbers with the usual successor is computable presentation of both, versus the sum of these two weird copies of the natural numbers, the L even plus the L odd, right? They're classically isomorphic, right? Both have order type omega plus omega, right? There's no computable isomorphism, but there's a classical isomorphism. So in particular, they're elementary equivalent, right? Because they're classically isomorphic. Yet if I were to look at any cohesive set C, the power of the first structure is going to be, well, the sum of the powers. So omega plus zeta eta plus omega again plus zeta eta, where then every element is going to have an immediate successor, right? But if I look at the power of the weird copy by any cohesive set C, whatever it is, again, I'll have that the power of the sum is the sum of the powers. Okay, and then depending on whether or not C was eventually contained in the evens or the odds, one of these two pieces has an element that doesn't have an immediate successor. Okay, so the point here was that, well, we've got two classically isomorphic structures, but it's impossible to make them isomorphic or even elementary equivalent via a cohesive power. Okay, so the Keesler-Shalat theorem doesn't work in this situation, right? And it also breaks the other way, right? You can have two non-isomorphic structures that always give you, or two non-elementary equivalent structures even, that give you always isomorphic powers, at least by delta 2 cohesive sets. So you can break the Keesler-Shalat theorem in all kinds of ways, and if you want it to hold, right, you have to have your structures be decidable, or do the cohesive power construction relative to the theory of the structures. Okay, right. So we saw that different things can happen, right? If you take the sort of default presentation of omega as a linear order, then you get the omega plus zeta eta order as its power. And we saw that you could get things that are different, right? And now we want to dig into that a little more and see if we can sort of achieve specific targets as the power, right? Not just get things that are different, but get things that are different and say exactly what they are. Okay. So the starting point for this is this theorem here. So this is now where I'm going to restrict to delta 2 cohesive sets, delta 2 definable cohesive sets. So if we do that, then you can compute a strange copy of omega as a linear order, right? Again, classically, but not computably isomorphic to the usual order on the natural numbers, such that no matter what delta 2 cohesive set you take, the power is always going to give you order type omega plus eta, right? So not omega plus zeta times eta, just omega plus eta. Okay, and this is as good as you can do for this kind of theorem in terms of the complexity of the cohesive set. Okay, so here's an example of something specific that's different that we can get. And then once you have this, you can generate all kinds of other examples. Like, what if I were just to say triple every point in this weird copy L, right? And look at the linear order 3 times L, right? So this here with k equal to 3. Well, if I triple every point in a copy of omega, I still have a copy of omega. Okay, so 3 times omega is isomorphic to omega, right? And then the result of the power is going to then also be that I triple every point, and I wind up with a order of type omega plus then 3 times eta. Okay, so omega plus dense copies of 3. All right, and I could do this equally well with 4 or 5 or 6 or whatever. So for every k, right, I've got a computable copy of omega that gives you power omega plus dense copies of k when you do the power via any delta 2 cohesive set, right? And these are all pairwise non-elementary equivalent, right? K time or 2 times eta is not elementary equivalent to 3 times eta, right? Because saying there's a block of size 2 is different from saying there's a block of size 3. Okay, so now we have a lot of examples of all different presentations of the same structure that give you non-equivalent powers, not only by any like fixed delta by any delta 2 cohesive set, I guess I want to say. Okay. Right. So it's I sort of phrased this as we wanted to fix a cohesive set to begin with, but actually we don't need to. It's one, you know, for each k, it's one copy of the order that works for every delta 2 cohesive set. Okay. Right, so we can make a lot of weird stuff happen here, which is quite different than the classical situation. Okay, right, and then how far can you push this kind of thing, right? We've seen that well, if we're looking at weird computable presentations of omega, right? Well, the usual one gives you power omega plus zeta eta. We just saw we can get powers of order type omega plus k times eta, right? Can we get other things? And yeah, we can get more stuff, right? We can get omega plus shuffle sums, right? So instead of omega plus dense copies of 2 or dense copies of 3, we can get omega plus dense copies of 2 and 3 as a cohesive power of a computable copy of omega. All right, and so the best we can do is the following here. Okay, so what patterns of finite linear orders can we shuffle in? And the theorem says that if I have a Boolean combination of sigma 2 sets, right? So X is a Boolean combination of sigma 2 sets, and I'm thinking of these numbers in X as finite order types. So if I have that, then I can compute a weird copy of omega, whereby any delta 2 cohesive set, the power is going to be omega plus dense copies of those finite order types from X, plus if the X is infinite, this one extra order type, omega plus zeta eta plus omega star. Okay, so omega plus shuffle 2, 3 is the X equal 2, 3 case of this, for example. And so this one here, omega plus zeta eta plus omega star, right? If you think about it, this is going to be the order type of the product of all finite orders. So it shows up naturally when you try to shuffle in an infinite collection of finite natural order, finite linear orders. Right. So if the X itself is finite, then you can get around shuffling this one in. But so far as I know, if you try to shuffle in infinitely many things, you kind of naturally also shuffle that one in. Okay. Right. So this was more just seeing how far this kind of construction can go and how weird can we really make this. Okay, so these orders here, though, all have computable copies, right? Even though it looks like a weird order as far as taking ultra power like construction of just the simple natural numbers is concerned. In terms of computability, they're not complicated, right? These all have computable copies, right? There's a computable linear order with order type this for any sigma 2 or indeed any sigma 3 set X. Okay, so this sort of raises the question as well: can we go so far as to get something non-computable, right? I mean, the whole cohesive power setup, right? The idea is that it's supposed to be a more effective ultra power, ultra product like construction, but it's certainly not completely effective, right? There's lots of non-effective stuff here, like the cohesive set itself is not a computable thing, right? So you would expect you should be able to generate some non-computable structures as powers of things. Okay, so where are we, right? If we have a sigma 3 X, then this order type here, omega plus dense copies of the orders in X plus this thing, right? There is a computable copy of that order type. But if you were able to go up to, say, a properly pi3x, then that wouldn't have a computable order type anymore, just because of the complexity of saying what the size of a block is. Okay. But we don't know how, but for this construction, we don't know how to go any farther than this, right? So that's a question. Can you get more complicated x's than just Boolean combination of sigma 2 sets, right? Could you shuffle in a properly pi3 set x, for example, into the cohesive power of a computable copy of omega? Okay. And if you could, then you'd have a non-recursive, non-computable order type appearing as a cohesive power. Okay, so there's lots of questions you can ask based on this. Like that would answer the previous slide, right? That would answer the question, is there a computable copy of omega where the powers are always non-computable, say, by every delta 2 cohesive set? Right, so that's like that would answer this first question here. Okay, but you can generate weaker versions of this question. For example, could you have a computable linear order? A computable linear order, not necessarily of type omega, just any old computable linear order where there are non-computable cohesive powers. Or even weaker, can you uniformly compute a sequence of linear orders where the cohesive product has always non-computable order type? Okay, and for this last one, at least the answer to that is yes. So I'll just say a little more specifically what the theorem is here. Okay, so you can have a uniformly computable sequence of linear orders such that when you do the cohesive product of that sequence by any cohesive sets, not just delta 2, any old cohesive set, the result is not elementary equivalent to any computable linear order. Okay, and for this we sort of adapted a diagonal strategy for diagonalizing against computable linear orders from Jakash and Soar. Okay, so it is possible to get non-computable things out of this in the world of linear orders, but a lot of questions remain, and this just says there is one that's not. There is one that's not computable, but it doesn't say anything about how not computable it is. We'll lastly look a little more closely at that, but not just for linear orders, but for any kind of structure, or maybe just graphs, which is somehow the most general kind of structure. Okay, I guess I should. So for this kind of question, coding stuff in or getting non-recursive things to come out, linear orders are a tough kind of structure to work with. So if we go to more general structures, things will be easier, and we can say more. So that's what this is about. Okay, so we showed that, well, at least we can get a cohesive product of something, linear orders, where the resulting power doesn't have a computable copy. Okay, and then we can ask, well, just in general, how complicated do these structures resulting as powers have to be? And right, okay, so these powers were made out of the computable structure, right, the partial recursive functions, and the cohesive set C. Okay, and well, if your cohesive set itself is more complicated, then the power might be more complicated. So for analyzing this, let's just restrict the complexity of the cohesive set, and we'll look at only like zero jump computable, right, delta 2 cohesive sets. Okay, so I've got a computable structure, I've got a delta 2 cohesive set. I want to know how complicated it is to come up with a presentation of the power. Okay. Okay, so if you just write down what all of these formulas say, then you'll discover that the power has a delta 3 presentation. right? So this means zero double jump computable, right? So zero double jump can compute an isomorphic copy of the power encoded over the natural numbers, right? That's what I mean here. It's a zero double jump computable copy of the power if you start from a delta 2 cohesive set. Okay, so and I wrote down a bunch of formulas explaining this, but we'll just go past them. Okay, so in the world of delta 2 cohesive sets, right, there's always going to be a delta 3 presentation of the power. And if you go to a general enough kind of structure, right, say graphs, if we look at graphs, then we can achieve that maximum complexity. Okay, so specifically, there's a computable graph such that for every cohesive set, every presentation of the power of that graph computes back for you zero double jump. Okay, so this says that zero double jump is a type for powers of computable structures by delta 2 cohesive sets, right? Because every presentation is gonna, or every power is gonna have a zero double jump computable presentation, but then also every presentation computes back for you zero double jump. Okay, and this is, I mean, so graphs are much easier to work with than linear orders for this kind of coding. So this is not really very difficult, but I'll just sort of give a hint about what the encoding is, and then we'll be done. Okay, right. So the basic idea is that I want to code sigma 3 facts about arithmetic into sigma 1 facts about this graph that is going to arise as the power. Okay, right. And the point of that is that well, both zero double jump and its complement are sigma 3. Okay, so really what I'm doing is making zero double jump join its complement computably enumerable in all presentations of my power graph. Okay, so that means I can list out the things that are in zero jump and also the things that are not in zero double jump. Okay, if I knew a presentation of my power graph, and therefore I know exactly what's in and what's out, so I can compute zero double jump from any presentation of the power graph. Okay, and the way that the encoding works is that I'll have my sigma 3 formula that I'm going to trying to encode into the power in an RE in a sigma 1 way. Okay, and I compute my graph so that the power will have a special vertex A, where the length of the cycles at A sort of enumerate for you the Ks for which this sigma 3 formula hold. Okay, so in the end, the encoding is that, well, my formula is going to hold for some K if my A lies on a cycle of a particular length, right? Pair KL plus 3 for some L, right? So the lengths of the cycle at A will tell you the Ks for which the formula holds. Okay, and this is not so difficult to arrange. That's just the basic idea there. Okay, so thank you very much. That's all I wanted to tell you. Just some little story about these effective ultra powers, these cohesive powers and cohesive products. So thanks so much for joining.
Okay, so thank you very much for the interesting talk. Some questions maybe. So maybe I want to ask a question. Could you please show slide 29? Thank you. So do I understand correctly that here the isomorphism type of the cohesive power, it depends on the choice of a set in this theorem?
Yeah, as far as I know, I don't think it's that every cohesive set gives you exactly the same power. It could be that different cohesive sets give you different powers, but the sigma 3 thing is coded in the same way in every result.
Yes, but so how to say this? Because I wanted to ask maybe a different question. So consider the following problem. Say we fix some computable graph, yes, and we look at all the isomorphism types of the cohesive powers if we restrict, of course, cohesive sets to, say, delta 2 sets. Can you get some like bounds on index sets of this class or something like that and show that this is optimal? Because in general, the isomorphism type, yes, depends on the choice of a cohesive set.
Yeah, I don't know. That's a good. I've tried to look into that. They get very different stuff depending on what graph. Of course, it could be trivial or so. Say one more time. You want to look at
like which particular isomorphism types could be realized as cohesive powers? Like what is the complexity of this class of isomorphism?
Oh, I see. Which so like of the delta 3 graphs, which ones arise as powers?
Yes.
Yeah, that's a good yeah, I don't have any information on that. I know not exactly that question, but I looked at sort of that style of question a little more with the powers of copies of omega, because there we do know like a little bit more of what the power has to look like the condensation has to be dense, for example. But for graphs, yeah, I don't really know any facts about like, oh, every cohesive power of a graph has to look like such and such, and therefore such indices are possible and such not.
Okay, thank you. And maybe one more small question. Could you please show slide 22, I think? Yes, yeah, thank you. So I was wondering, like for the first, sentence here, does it matter that we have a finite Boolean combination, or maybe it could be pushed a little bit further in the difference hierarchy, say kind of analog of omega CE with respect to zero jump? Could it be pushed?
Yeah, that's a good idea. I didn't. No, I didn't. I haven't thought about that. No, that's a good. Yeah, maybe more reasonable, like next step, I guess, between Boolean combinations of sigma 2 and sigma 3 or something.
Okay, thank you very much. So
yeah,
maybe
good. Yeah, thanks for the ideas.
Maybe some other questions. Okay, so if no questions, then let's thank Paul again. Yes. And
thank you.
Yeah, we thank all our speakers and we thank all the participants of the workshop. And maybe Manat could also say like some final words.
Yeah.
Yes.
Thank you. Thank you all the speakers for nice talks. Thank you, Paul. Thank you, Kyle. Thank you, Tatyana. And thank you for all the audience, and happy Logic Day for everyone.
Yes, happy World Logic Day, and we hope that we will meet next year also at the next workshop.
Yes. Okay.